Hi everyone, I hope you're enjoying the meeting so far. In my presentation today, I'll be talking about different space weather forecasting needs that are, however, viewed under a common prism. Why are we doing this? We're doing this because we believe that we can achieve improved space weather forecasts in this way and at the same time enhance the physical understanding of the system that we are studying. So my presentation right here is a collaborative work that is being undertaken by Georgia State University's data mining lab. The people that you see in there are affiliated to the lab more or less. And here I have a number of items that I will be briefly touching upon in my presentation. I'll be talking about verification, as you can see over here, but not only about performance verification that many of us are only talking about. I'll be talking about data and model verification on equal footing with performance verification. I'll be talking about benchmark datasets as the means for achieving these different verification tasks. I'll be giving a couple of examples of benchmark datasets in solar flare prediction, how we can enhance these datasets horizontally and vertically, and what can these enhancements, these improvements can help us do. And finally, I'll be putting everything together under a concept for forecasting of solar energetic particle events that is underway at the data mining lab again. And we believe that we'll be able to have some interesting forecasting results from this system in the future. So in this set of pictures, I am providing the what I call the solar end of space weather, in which we have the different phases together. Not different problems, but different phases. Because flares, solar energetic particle events and their CME sources are in essence different phases of the same fundamental eruptive space weather, solar weather problem. So this is how I think they should be treated. They correspond to a possibly stratified physical space, but there are certain interconnections between the different layers of this physical space, so it is in our best interests to have these problems treated jointly. So in this respect, if we were interested in a joint treatment of these problems, what we would care about solar flares, for example, we would care about the class, the size of the flares before they actually occur. We would be caring about their association with coronal mass ejections, at which case we would be interested in the time of arrival of CMEs and the geo-effectiveness of these CMEs. And of course, in case these CMEs were fast enough with shocks, we would be interested at solar energetic particles events at geospace in regards to their time of arrival, the flux and the fluence of protons, and the temporal profile ideally. Even in case we do not have CMEs, we might have some SEP events much short-lived and impulsive associated to the flaring locations. We might be interested in those as well in terms of flux and fluence. So how do we tackle these different problems together? I'll start from the basics. If we have a theory, what is a theory? A theory is a set of concepts and ideas that is being used in order to make testable predictions. So we have a theory, we apply it to our favorite problem. In order to apply it, we need both some data, some appropriate data, and a model, a forecast model in this case, right? So if we have the data and the model, we can run the model on the data. And then we have the verification tasks to make sure that the whole system performs as it should. But this is not only about the performance of the model. This is both about data and for the model itself alongside the performance. So the verification is a much broader task than simple performance verification. How do we do that? Well, we have what we call benchmark datasets. Just to give you a tentative definition here, these are an integral part of data mining where new techniques and algorithms are tested against some arguably high quality data sets, so some data sets that have been curated in such a way as to demonstrate the reproducibility, effectiveness, and efficiency of the models that are tested on these data. There are some platforms already out there, such as the Kaggle platform and the ImageNet platform, and most recently the EarthCube platform in geosciences that includes several benchmark data sets where different models can be tested. So in essence, what do we have? We have three tasks. We have the benchmark data set itself. We have the second task, which is pretty much what we call BYOM, bring your own model, in which case we take models and we apply sanity checks to make sure that they perform the way they should. And then in the third task, we run these models on the benchmark data set and verify their performance by means of multiple skill scores and statistics that we have for verifying performance. So all in all, we build experience and we transform this experience into something that is tangible, into knowledge that is tangible and can be used, right? So that's an example of a benchmark data set in solar flare forecasting. It corresponds to the European Union Flarecast project and is readily available in there. This is solar cycle 22 data, more than 29 metadata parameters of active region properties in the solar photosphere, more than 5,500 integrated flares of Gauss class C and above. This is the website with the API and application programming interface where these data can be freely downloaded. And there is a paper, of course, that hopefully is going to be out soon and will give all this information about this data. Then a second example that we have at the data mining lab at Georgia State is what we call the space weather analytics for solar flares. What is this? This is a partitioning of solar cycle 24 into different samples. Each of these samples, each of these partitions has the same size, the same population or similar population of the positive class of major flare instances and everything. We have more than 9 years of data, 51 metadata parameters, full cadence time series at 12 minutes, and more than 13,500 flares integrated in there. These are all available at Harvard Dataverse, and you can read everything in a recent paper by Rafal and Greek et al. In Nature Scientific Data. And this over here is what we say, what we call the flare butterfly diagram, in which case you can see that we have pretty much covered homogeneously the entire solar cycle 24. And then if we have the benchmark data set, we can apply, as I said, an arsenal of skill scores and statistics in terms of performance verification. Different efforts over here. This is a community supported effort to test different operational flare prediction models by KD Leka and Company. This is what we developed in the Flarecast verification engine, and this is an effort by the GSU data mining lab in regards to class imbalance in the problem. This particular type of study can only be achieved by means of benchmark data set, not otherwise. So this is the existence of benchmark data sets is pretty important in this respect. So let's say we have a benchmark data set, such as the examples that I showed you in regards to flare prediction, then we can expand these data sets. How? Both in terms of horizontal expansion and in terms of vertical expansion. By horizontal, meaning that we add more parameters, more predictive parameters in there, and by vertical means that we diversify our problem into additional phases of space weather forecasting. For example, we have the flare integration problem here and the flare forecasting. What we can do is that we can split it into an eruptive flare identifier and a confined flare identifier, in which case we can apply a vertical expansion to our benchmark data set to do what? To do CME forecasting. and we can further extend this CME forecasting into fast CME forecasting. So we're looking for CMEs that are capable of generating shocks. How can we do that? There are recent works in this respect. This is a flarecast work by Yannis Kontoyannis et al., in which case they were able to associate projected CME speeds with photospheric active region metadata parameters at pretty decent, or I would say high, correlation coefficients. This is a work at the data mining lab at Georgia State, in which case we might be able to associate the length of polarity inversion line in the active region photosphere with CME speeds and CME existence in general. Putting everything together, what we have recently done at Georgia State University at the data mining lab is that we presented a concept of solar energetic particle event forecasting going back all the way to the solar sources. And in order to deal with intrinsic ambiguities and the interconnection between different physical spaces, we have a concept of forecasting SCPs in two tiers, in two different levels. One is the watch level and the other is the warning level. What is this? This actually borrows terminology from extreme terrestrial weather, such as tornadoes, for example. An SCP watch means that there is at least one active region in the Earth-facing solar hemisphere that is capable of giving an eruption that is associated with SCP events. The second is the SCP warning phase that tells us that an eruption is in place, in which case we should be expecting a CME. And we have different protocols, different ways to actually validate and deal with both the forecasting and the verification and the validation of each of the different two phases. Then our SCP sample goes back 20 years in time, about 206 SCP events over here. We have 123 events that have a solar source association over here, and you can see how the sources of these SCP events are distributed over the solar cycle. Here we have some statistics that investigate different class imbalance phases of the problem, and here we have some numbers in regards to this, how SCP events relate to flares and CMEs. All this is groundwork that we're going to be using in order to be able to achieve some meaningful results over here. And this is a blueprint, pretty much. This is a blueprint of the implementation of this SCP watch phase. Initially, how we deal with SCPs. So we're dealing with the data collection, the collection of active region metadata, flare prediction, eruptive flare prediction, CME velocity indicator, probabilities of flare in here. And from that, we can go on and make an SCP forecasting in terms of SCP temporal profile, peak flux and everything, or we could come up with an all-clear prediction. So these are my conclusions pretty much. The first one is pretty important. It tells us that space weather forecasting is a real-world problem, and moreover it is a formidable one that diversifies into different phases at different spatial and temporal scales. There is a temptation to achieve treatment of these problems by identifying different phases as different problems. This is not what we think is the most appropriate action here, the most appropriate approach. We should be able to tackle the problem simultaneously to the extent possible. But in doing so, we need benchmark data sets and we need verification for both these data sets, for the models that we are using and for performance. Benchmark data sets, as I said, are important, but they can also be enhanced. We can build from there in order to achieve further forecasting goals in there and targets. And finally, we can show how we can pursue a unified treatment of solar flare, fast CME forecasting, and SCP event forecasting. These are just initial phases, but we hope to have meaningful results to show in the near future, more or less. So just to give you an idea of what I talked about, you can look into this list of papers over here. They correspond to different aspects of the problem that I just talked to you about. And that's pretty much all I have at this time. Thank you for listening and enjoy the meeting. Thank you.